We focus on the task of semi-supervised node classification. Given a graph with feature vectors for each node and a few labeled nodes, our goal is to find the class label for each of the remaining nodes. In recent years, graph neural networks have shown to be effective in this task and have gained wide research interest. However, many existing GNNs rely on the homophily assumption, which assumes that the linked nodes are similar. We can use an idiom to explain what is homophily, that is, birds of a feather flock together. However, there are also graphs which go beyond homophily by showing heterophily, or in idiom, opposites attract. Existing GNNs have largely overlooked the settings of heterophily. At a high level, in this work, we review current limitations of GNNs in heterophily settings. We present and theoretically justify a set of key designs that boost learning in heterophily without sacrificing the performance in homophily. And we conduct extensive empirical evaluation across the full spectrum of low to high homophily to show the effectiveness of the identified designs. As a motivating example, we test some wide-adopted GNNs in heterophily and observe that in some cases, all existing methods fail to perform better than multilayer perceptron, which is graph-agnostic. This reveals the challenge of popular GNN models to effectively leverage graph adjacency information in heterophily. Motivated by this limitation, we identify a set of key designs that can help improve the representation power of GNNs in heterophily, and theoretically justify them in our paper. These designs include separation of ego and neighbor embeddings, utilization of higher-order neighbors during aggregation, and combination of intermediate representations. By combining these identified designs, we introduce a GNN model named H2GCN, which we use as the base model to study the effectiveness of each design in different levels of homophily. We find that in synthetic networks, the identified designs helped H2GCN perform up to 40% better in heterophily compared to the variants without them. In real networks, we also observed that methods with these designs perform up to 27% better compared to vanilla GCN while maintaining competitive performance in homophily. These findings confirm our theoretical analysis and support the effectiveness of the designs. Thank you for listening. For more details, please join our poster presentation or check out our paper.